Good morning, everybody, and afternoon to some people, and welcome to today's webinar, Electrical Safety Testing, a Complete Overview Part 1. This is a new webinar for us. It includes much of the same material you may have seen in the past, but what we've tried to do this year is revamp quite a few of our webinars. The template has changed, and some of the information has changed as well. Excuse me. Something else that has changed is who we use for our webinars, and I just wanted to give everybody a heads up that we switched over to GoToWebinar. So far, everything's been working out really well, and we think we've worked out most of the kinks, but just bear in mind, like stuff like that. Bear in mind that there could be a couple hiccups throughout the webinar. Shouldn't be anything huge, but if you do have questions that pertain to your ability to hear me or see what's on the screen, use the Q&A utility on your GoToWebinar bar there and let Jim know. Jim Kennesy's our organizer, and he'll be able to help you out with that. Any questions related to the material itself, use the chat utility and direct your questions to Syed Abidi. Syed is our applications engineer. He's very knowledgeable, and he will be able to help you out with those questions. At the very end of the webinar, I'm hoping what I usually do is I leave a few minutes open in case there are any questions we really couldn't get to during the webinar for any reason, or questions that Syed feels might be pertinent for the entire group to hear. So I'm hoping this will take only about 40 to 45 minutes. I like to keep it open for some questioning, and then we can use that extra time to answer those questions. Now, should we not get to your question, or your question is kind of in depth and we really can't cover it during this time period, you can always feel free to email us directly. You have Jim's email right there, and you can also email us at info@asresearch.com. I will be giving that email again at the end of the webinar, so just keep that in mind. This webinar is being recorded and will be available to view usually within a day or so, and you can get that directly from our website on our webinar archive. And then if you do want copies of the slides themselves, just let Jim know, and he can send you over a copy. That being said, let's get started. Now, we're doing this particular webinar in two parts. In the past, it was one webinar, but we really feel that this is too much information to cover in one one-hour webinar. So we split this into two little ones. We got this complete overview, part 1, and then part 2. Part 1 really covers the safety aspect of things, whereas part 2 starts to talk about the tests themselves. So they're both important to view. If you think one is more important than the other, that's really not the case. Yes, it's important to know what the tests are and what they do, but it's just as important to know about a safe testing setup, as well as training resources for your people, which we'll be talking about here today. So we're just going to talk about general safety, what's a safe workstation, how you can set it up, why you would test in the first place, the different types of testing, methods for safety testing, and there's various methods you can use. Obviously, we understand that there are going to be all different types of production floors, laboratory setups. If there is a difference in these different setups, you name it, we can try to cover it here in this webinar. And then, of course, we'll cover some extra training resources for you guys, give you some links to help you go through and supplement the material that you've gone over here today. So just in general terms, what is safety? Basically, the definition is the condition of being safe from undergoing or causing hurt, injury, or loss. When it comes to what we're talking about electrical safety for the most part, but we can also deal with fire hazards and things of that nature. So a device or a machine designed to prevent inadvertent or hazardous operation. And that second point is really what I'm going to hit on today. What can you guys do in your setups that's going to help somebody from getting hurt or injured? And there's a lot of ways you can do this, just as many ways you can do it as there are different setups and production floors. So let's talk briefly about shock hazards, because anybody who's ever used our equipment knows, well, we deal with electrical safety testers. So your primary hazard here is going to be an electrical or an energy hazard. There's a couple different potential shock hazards, actually 3 separate ones that we cover here that cover actually a wide range of potential shock hazards. But the first one is that contact is made with one point of a circuit and ground. And as you can see in that image there, we basically are showing an energized chassis, and then that person is at a ground potential, and you can see it's flowing through their arm, through their body, and out their foot to ground. It can also happen where contact is made with a hot metallic part while the person is at ground potential. So you don't need to necessarily just come in contact with something like a line conductor. Let's just say that you have a large chassis, a large metal chassis on a device. Let's say internally on that, one of the live energized conductors is frayed, and it is now contacting the chassis of whatever machine this might be. Well, if you come into contact with that chassis and you look like a low resistance path for the current, it's going to go through you. One thing to always keep in mind is that electricity is very lazy. So it's going to take the path of least resistance. Putting yourself at a ground potential makes that path very attractive to electricity. So there are ways that we can help with this. No matter what, there's going to be incidents where wires get frayed and there is an energy hazard. But we can try to mitigate that as much as humanly possible. However, you don't always have to be at a ground potential for there to be a shock hazard. Contact made between 2 points of a circuit is also a shock hazard. As you can see there, the person is not at ground potential, but they are a low enough resistance path that across those two hands, the current decides, hey, this looks like a low path, I'm going to take this direction. Excuse me. That path is actually particularly bad because you're going through the chest cavity. And there are different effects depending on the level of current and voltage that electricity will have on the human body. And we're going to cover that in a few minutes. So let's take a look at effects of electrical current on the body. Now, one thing to keep in mind while I'm talking about this information is that these are for effects of voltages less than 600 volts. 600 volts is right about the breakdown voltage of skin. So that's why this term, that number is used here. Many of the electrical safety testers out there, ours included, can output voltages in excess of 5,000 volts. Some of ours do more. We can go up to 20,000 volts AC and DC. The point is that at a much higher voltage, these numbers are going to be reduced. Those effects at these high voltages have not been studied in depth, which is why we haven't provided these numbers. But I think these numbers provide you with a really good base of what you need to look out for. It doesn't take a lot of electrical current to cause a problem. For example, 0.5 milliamps to 1 milliamp is right about the perception level, meaning that's when you would start to feel it, a tingle or maybe something just akin to a tingle if you were to come in contact with a live conductor. When you jump up to about 5 milliamps, and this could be even less in some people, keep in mind these are not hard set numbers. There's ranges of numbers. It's different for every person. At 5 milliamps, you could have a slight shock felt, and at that point you could have what we would call a startled reaction. I'm sure many people who are listening to this, myself included, accidentally at home, when you're messing with something electrical, you're plugging something in, maybe your finger came in contact with the live part of your blade on your plug, you get a little zap, and it kind of gives you that little startled reaction. And now that in and of itself might not be very dangerous, unless you have like a pacemaker or something along these lines. But the startled reaction can cause a problem, because what if you're in a situation where you're in a cramped space and you're doing electrical work and there's moving parts around you? That's really more the danger there, that the startled reaction causes your hand or your arm to go into a different space that could have a mechanical hazard, or yet maybe even another energy or a chemical hazard. So these are things to consider. So usually my line there, about 5 milliamps, is where you really got to start to pay attention. That's also right about where household GFIs kick in, and it's just for that reason. Now when we jump up, and this is a very wide range, and it's different for men and women as well as people with different body compositions, and that's something I really can't reiterate more. I don't want to beat a dead horse or anything, but you got to understand that there are ranges here. These aren't hard set numbers, but they do give a good base as to what to look out for energy hazards. When we go in the 6 to about 30 milliamp range, that's when you're going to get a painful shock. And in the higher end of that range, you might even have the inability to let go. And that's really where we're entering a danger zone, so to speak. Because if you can't let go, you're going to have a different way to release somebody from the circuit, whether that be an e-stop that completely cuts off power or somebody else releasing you from the circuit. It's going to require some type of intervention. And that's why in these ranges, it's more important than ever to have as many safeguards as possible when you're dealing with this type of electrical energy. When we jump up into the zone after this, this is when it can really get life-threatening. Now keep in mind, it can be life-threatening below this range. If you have somebody who's in a weakened physical state, has a pacemaker, had some kind of heart complications in the past, shocks below 30 milliamps can be fatal. So I'm not saying they're not. But in 30 to 150 milliamp range, this is extremely painful electrical shock. This is when you can go into a ventricular fibrillation, respiratory arrest, and death is possible in this range. And then, of course, if we're jumping up anything past this, 1 amps, 10 amps, whatever, you're talking about severe third-degree burns and cardiac arrest. So death is almost certain when we're talking about this range in these voltages of about the under 600-volt range. Now, a lot of the voltages that I'm talking about, I say under 600 volts, but I'm really talking about household voltage, like your 120. If you're in Europe, 230, maybe 220 or 240 volts. Now, where did they get these numbers from? Well, this is an abstract from Underwriters Laboratories, and it was written a while back, but they did a study where they basically had volunteers, believe it or not, people volunteered to do this, where they'd put their hands on opposite copper plates, and then they would store a charge in some caps, and they'd release the charge, and they would see how people would react to these shocks. And that's how they kind of got some of these numbers at 60 hertz. And 60 hertz is actually, 50, 60 hertz is more dangerous because it actually interferes with how the heart works. I'm not a doctor. I'm not going to go into the ins and outs of that, but right about up to 100 hertz is a really dangerous range because of how that affects your heart muscle. So when you get beyond that, it's actually not as dangerous in many cases. But since most of our stuff does operate at 60 hertz, you have to be especially careful. Also, most high-pot tests or high-potential dielectric withstand tests, since your products run at 50, 60 hertz, you got to run your test at 50, 60 hertz, which ups the danger because in those cases, you're dealing with a much higher voltage. So I just wanted to give you guys a little bit of background on where did they get those numbers in that table we were looking at. Well, here you go. As you can see, they used Abraham Lincoln and put his hands on copper plates so that they could study how this happened. So let's look at human body resistance here, because this is important into how to mitigate shock, is to really understand what's going on in the human body when something like this happens. Now, on average, the human body has about 1,000 to 1,500 ohms resistance to the flow of electrical current. Now, I will say that that is a conservative estimate. When I say conservative, I'm kind of saying worst case, because that assumes a pretty large contact area. That is basically I would be grabbing a metal conductor with each hand up the size of a Coke can, so complete contact with the hand. It also assumes a much lowered resistance. Maybe my hands are wet. If you wanted to run an experiment on your own, if you have a simple LCR meter, go ahead and put it in just DC resistance and grab one side with one hand and one side with the other, and you'll see usually it's much higher than that. Fingertip to fingertip contact, I just did this the other day, and I got about 500,000 ohms. But if I lick my fingers or lick my hands and put it on there, it goes down to 100,000, maybe 50,000. So you can see just that wet surface will provide a much lower body resistance. And that's why I say to keep in mind that different conditions are going to have a great effect on how much current you're actually exposed to. So the outer layer, or your skin basically, this provides the largest percentage of the body's electrical resistance. It's a barrier. It's helping you. It's keeping you from being exposed internally to this type of current. But like anything else, skin is a breakdown voltage. And as I mentioned previously, you're talking about around 600 volts, at which it ceases to act like a resistor and is simply punctured, just like insulation. The problem with that is that your blood vessels, your body tissue, those types of things, they are very good at transmitting electrical signals. They have to be, because our body works off the electrical signals. So what is a strength with how our brain communicates with our body can also be a weakness when it comes to this, because if that skin is breached, you really don't have anything else to protect you against electrical shock, aside from the safeguards you might have at your station. So unfortunately for us, the parts of the body which conduct electricity the best are blood vessels and nerves. And you can see our little body model right there. A very simplified model, I'll say, because it's only looking at resistances, whereas the human body almost certainly would have a capacitive or storage element to it with the skin and then the different tissues. but looking at a very simple model, let's do some calculations. Let's just say we have hand-to-hand contact. That's about 1,000 ohms. And we come into contact with a European household 240-volt circuit. Using simple Ohm's law calculation, we see that that's about 240 milliamps. And as we saw from our previous table, it only takes about 100 milliamps to kill you. It's even less than that with somebody in a weakened state. So that just goes to show you that a household appliance or a household outlet has more than enough electrical potential to lay you out. So when it comes to something like an electrical safety testing station, you have to be extra careful because we're dealing with an even more dangerous situation. Now here's a couple different models with a couple different calculations. As we can see in the upper left, this is where Abe Lincoln is exposed to 240 milliamps, your hand-to-hand contact. What I show there in the upper right is fingertip to fingertip. And that's just what I was talking about before when I was relating contact area. As I said, I did that experiment before where I went fingertip to fingertip on a meter, and I got a much higher value than 20,000 ohms. I'm using, again, a worst-case scenario conservative number here. But even just fingertip to fingertip, you're still talking about 12 milliamps. You would definitely feel that at standard household voltage. If you have a high pot tester at 12 milliamps, you're definitely going to feel that. Trust me, it's happened to me. Then if we look at that bottom model, that's assuming that it goes through the body cavity. So a little bit more resistance, but you're still talking 218 milliamps. That's a lot of current, and you're still in a dangerous zone there. So that gets us into the testing in general. Well, up to now, we've been talking about human body impedance models, how shocks are going to affect you. Now we really start to want to get into the testing itself, the testing station, but why are we testing in the first place? Why do we run a high pot test or a leakage test or a ground bound test on our products? Well, there's four main reasons. There's more than four, but I can break these down into four main reasons why we should test products prior to shipment. First and foremost, the number one is safety. We want to ensure that a product is not going to pose a hazard to the end user. Basically, if you plug it into your wall, it should be tested. We want to make sure that when somebody uses the thing, it's not going to kill them. People always ask me, what do I do for a living? And to just simplify it, I say, hey, anything you plug into the wall, our machines that we make sure that when you use that, it doesn't kill you. First and foremost, safety. Second is quality. You want to be able to detect workmanship defects and prevent faulty components from being installed. The high pot test, which we're going to get into in the next webinar when we have part 2 of the overview, the high pot test is a very versatile test. Not only will it detect safety issues, it also has the potential to detect quality issues. They might not necessarily be a safety hazard, but they can tell you if something's installed improperly. 3 is cost control. You want to be able to identify a problem before a product is shipped. Because if your product goes out there and somebody gets hurt, you better believe there's going to be a recall. I've seen it in many instances. You could go on websites right now, U.S. government websites, and look at product recalls. It's not a short list. So it's imperative, it's very important that these products be tested for integrity, especially insulation, grounding materials, before you ship it out. It's going to save you a lot of money in the end. Even though testing can be an expensive endeavor, it's well worth the upfront investment. And then, of course, what flows from that is liability. You want to protect product liability suits because the responsibility of performing the electrical test ultimately rests on the manufacturer, you guys. It rests on you guys to perform these tests. And it's going to come back on you guys if it shows that a test has not been done properly. We've even run into situations where people thought they were doing their test properly, and then upon further review, it turns out that they weren't even running a proper high pot test. So, like I said, next time we're going to cover more of the testing itself, but that just goes into making sure not only that your operators are safe, but that they're doing the tests right. So this kind of goes into the testing laboratories themselves. Why are we testing in the first place? It's not only to make sure things are safe, but also it's what is dictated by many of these what we call NRTLs or testing labs. NRTL stands for Nationally Recognized Testing Laboratory. You guys, I'm sure, have heard of Underwriters Laboratories. You may have heard of TÜV Rheinland, the Canadian Standards Association, or CSA, ETL, or Intertek, and CCC, which is the China Compulsory Certification. Any device that goes onto the market should have a marking like this, an NRTL or Testing Lab Recognized Stamp of Approval. in some countries like Europe, it's mandated. I realize Europe's not a country. What I meant was the countries within Europe, it has to have at least a CE mark to be sold in the European Union. Now in the States, you don't have to have a testing lab certification mark on your product to sell it, but good luck getting into mass market if it does not have that label on it. Every one of our high-pot testers has a stamp from an NRTL on it. Products that you guys buy, including your safety testers, should also have that stamp. And I'm sure anybody who's listening to this also has the stamp on their product, because if you're listening to this, you're running this testing to help you get these marks of approval. These testing laboratories create standards that outline performance and production testing. They also implement and enforce electrical safety testing to protect users from potential electric shocks. It may seem like a pain to go through a lot of these tests, but it's for a good reason. These standards are laid out to guide you guys on how you should be testing your product, not only in the lab as a prototype test, but also as a 100% production line test. So the NRTL standards dictate that electrical products incorporate 2 lines of defense to protect the user from electrical shock. 2 main lines of defense anyways. There's others, but we don't have the time to cover everything in detail in this webinar. First of all, there's insulation. This is what we've been talking about. This is what the high-pot test checks. It separates power lines from your low-voltage circuits. It also separates power lines from your isolated power supplies, and it isolates input power from the chassis or case of an electrical device. I mean, just think about something as simple as a toaster. Many of the toasters out there, including the one I have at home, it's got a metal case on it. I like the stainless steel look. It's got a metal chassis. My toaster has a 2-prong cord, which means it's a Class 2 product, which means it has double insulation. And you can see that comparison in the bottom of this slide here, Class 1 versus Class 2 products. If I plug my toaster into the wall, I don't want line power going directly to that stainless steel chassis, because every time I use the thing, I would shock myself, which every time would probably be just that once, knowing how much line voltage can put through your body. I'd make that mistake once, and then I'd pretty much be toast. No pun intended. So anyways, the insulation is what's guarding you from getting shocked. But sometimes insulation fails. Your second line of defense here is safety ground. What this allows for is dangerous fault currents to return to the system ground. So if your insulation does fail, let's just say line voltage does go on your chassis, what this happens is fault current is going to flow to the ground pin in an attempt to return to the source. Anybody in your standard house, you have circuit breakers. This is why you have circuit breakers. If there's too much current flowing, it's going to show that this is happening. Your breakers are going to detect it, and it's going to enable the breakers to open to cut off power to that completely. This is going to more safeguard you against fire rather than electrical shock. That's really what it's designed to do. But it also protects for damage against the electrical equipment itself. Because if it kicks in within enough time, you're not going to melt the insulation on your product. Now, as I mentioned before, and I kind of already talked about this when I was talking about my toaster, electrical products can be classified according to the insulation type. The main ones are Class 1, Class 2. Again, there are others, but we're not really going to go into them in depth right now. A Class 1 product terminates in a 3-prong line cord, which basically is a line or a hot, a neutral, which is your return path for current, and a safety ground. That ground prong connects to your product's chassis, so that if something does happen, dangerous fault currents can flow back to ground without posing a hazard to you. Remember I mentioned before, electricity is lazy. So if you touch it and it sees a more attractive low resistance path to ground, it's going to take that path instead of you. So you basically have safety through basic insulation and proper grounding with a Class 1 product. Class 2 products are a little different. You see more and more of these in the household now. For example, your Xbox, your phone chargers. Like I mentioned, my toaster. A lot of household appliances now have, instead of a ground, they only have 2 prongs. There's no ground there. There's just a line in the neutral or a hot and a return path. The safety comes through a layer of dual insulation. So instead of just basic insulation, there is yet another layer of insulation to protect the user from electric shock. So there's a couple ways you can do this. And your testing is going to differ depending on what type of product you have. So if we're talking about electrical accidents in the workplace, and this is especially important when we segue into your safety testing setup, we really need to consider that most electrical accidents in the workplace are a direct result of one of these three or all of the above factors: unsafe equipment or unsafe installation or improper installation, an unsafe working environment, and unsafe work practices. I've seen one or more at many of the companies that I've visited. I've seen all at some of the companies I've visited when we go in and we look at a customer's setup. So it's not uncommon that somebody's making a mistake or could really do something very simple to safeguard it and avoid that mistake. Because these accidents really can be prevented through the use of insulation, guarding, grounding, electrical protective devices, and safe work practices and procedures. It's also really important that you don't take shortcuts. If you have a safety procedure in place, follow it to the letter. It may seem like a pain, but I've run into cases where guys got hurt, and it's because there were shortcuts. And they hate to say it, but you know, I've talked to guys who have admitted, yeah, if I wouldn't have done this, I wouldn't have gotten hurt, and boy, I wish I would have taken that extra 5 minutes. So a couple examples here. I like this picture a lot. As an example of unsafe equipment or installation, that is a rat's nest right there. You never want to open an electrical panel and it looks like that. Unsafe environment, I know this probably isn't the best example. It's not a production floor or anything, but I would say that's a relatively unsafe working environment right there. This guy probably shouldn't be doing that. That's posing a number of hazards, which I probably couldn't even list off in time of this webinar. And then unsafe work practices. This looks like a ridiculous picture, but you wouldn't believe setups that I've seen that are not too far off from something like this. I mean, you have exposed wires, you have exposed conductors all over the place on this picture. So I know I've provided some extreme examples here, but I just want to make the point that this does happen, and there could be multiple examples of it in your workplace. You might not even know it. So the easiest way to get around this, especially when we're talking about electrical safety testing, build safeguards into your station. Some of these safeguards are very inexpensive and really don't take a lot of extra time on the production floor. I mean, we understand that, you know, with a lot of our customers, you're pumping out thousands of products every single day, and having to build safeguards just adds extra time to that production line, because you got to build in the protection, make sure they're following those steps, and you have to test. And we understand that time is money. So we're here to try to guide you guys and let you know the easiest ways to do this for the fastest throughput and keeping your operators safe. So there's enclosures designed to remove a shock hazard. This is actually one of the easiest ways you can do this, if it's possible for you. Simply building an enclosure ensures that nobody can touch the product or device under test, or DUT, while it's being tested, because that door has to stay closed. And I'll show some examples of this in a little bit. Cabling and insulation. That little picture you see there are two probes that you could use for a high pot tester instead of clip leads. So if you have to test something that's very large, or you need to move around a lot to test something, you can use probes, which make you push those little buttons in instead of having to put your hands on the product. It pretty much ensures that you can't. But also using the proper PPE, or personal protective equipment. That's very important, and you should definitely look at your OSHA regulations to determine what personal protective equipment you need on your floor with regards to your particular work hazards and job functions. In that picture right there, these are different types of PPE that I commonly use in the lab. And I'm a very experienced operator, but I still use them if I at all can. You show a picture there of a guy with safety glasses. That's if something sparks, you don't want little pieces of metal flying around in your eye. High voltage gloves, which I use very regularly, and I have gloves that go up to 10,000 and 20,000 volts depending on what I'm working with. That picture also shows lineman boots. Not for everybody. You probably don't need lineman boots in all environments. It's never a bad idea though, because it's going to insulate you from ground potential. And then just being aware of all nearby hazards. As per OSHA regulations, qualified operators have to be qualified to work in their particular environment, and they have to have that training in order to do that. I'll provide you guys some links and resources later so that you can look up the information that we're talking about. as you can imagine, there is a wealth of knowledge out there, and we have by no means have enough time to cover it here. But hopefully, this webinar gives you good information about your testing setup, will guide you, and then point you in the right direction. So let's look at some methods for safety testing and some example workstations here. This is kind of what my lab looks like, aside from the production floor off to the right-hand side of the image there. So a couple things to notice here. You can see that you have a guy, and when I say positive protection, what I mean is the operator cannot contact the device under test while it's testing. As you can see where it's labeled A in the picture here, what that's meant to show is an enclosure over our device under test. You can see there's a motor labeled H there. So we're just testing a motor here. B is our high pot tester, or dielectric withstand tester, and A is an enclosure. And you can see the enclosure is directly linked to the high pot unit. It should be in such a way that the high pot unit is what we call interlocked. Most high pot testers nowadays have an interlock built in. In other words, you can wire it in such a way that if that enclosure door opens, your high pot test will not start or will cease outputting voltage mid-test. Basically, you have to have that door closed in order for the test to be run. That ensures, number one, that the operator can't touch the DUT while it's testing, and number two, should somebody accidentally bump an enclosure door or open it up to where there could be a live exposed conductor or a live DUT while there's a high pot test happening, the high pot test immediately stops and automatically discharges the unit under test. A couple other things of note in here. C is the operator itself, or him or herself. D is an insulation mat, which you can put on the floor. Insulation mats are a really good way, another good way to isolate an operator from ground potential. Because as we mentioned, ground potential could give you a low resistance path to ground, but if you insulate yourself from that, you're just mitigating the shock hazard. You'll also see we have E there is a safety light. So basically, that light would be illuminated red when your high pot station is in a ready state. You'll also notice G, or let's go with G first. I skipped a letter, but is basically a danger high voltage sign. Yes, the operator knows there's danger high voltage, but somebody walking by or working in the near area, or a visitor walking by, for example, they might not know what a high pot testing station is. So it's always a good idea to have high voltage signs up well away from the testing area to let people know not to walk in an area. Another way I've seen it done is tape on the ground, yellow or red tape that says danger high voltage that encloses the entire testing area. And then, of course, there's an e-stop switch in that entire station. E-stop switches are usually wired up to station power, not just the high pot tester, the whole station. So if there's a problem, somebody's getting shocked, somebody can walk by, slap that e-stop, and it cuts off power to the entire testing station. You'll notice that I have some markers there, a 10-foot marker. The reason I put that in there is per OSHA guidelines. If you are somebody who is not qualified to work in an electrical safety testing setup, the minimum approach distance for a workstation like this is 10 feet. So you should not have production operations near testing operations, because if somebody gets too close, there is the potential that they could come into contact with a dangerous situation. 10 feet might sound a bit excessive, but that is the standard guideline for that. So as you can see, what I've shown here, labeled I, is a production or setup operation well away from your testing operation. Now we understand that not every station is going to be able to use positive protection. You could be testing something very large where it's just not feasible to enclose it completely with something like a glass or plastic enclosure. So in those cases, there are still other things you can do to protect yourself. Here's a testing station without positive protection, and all I'm showing there looks like a dryer, something basically way too large to feasibly be put into an enclosure. But as you can see, and I actually based this model off of a customer that I went to. They had an excellent testing setup. So you can see that it's entirely fenced off. There are danger high voltage signs at every side of this setup. Now, in their setup, obviously the high voltage signs weren't all facing the same direction. This is just to give you guys an idea. And the door to the testing station also had a danger high voltage sign. You can see e-stops labeled F in both corners of the setup. You can clearly see a couple lights, one mounted way above in the upper left-hand corner there, and then one by the test operation or the setup itself. Both So if somebody's walking by and they see that light's red, they're probably not going to go near that gate. And as you can see labeled H, there's a gate there. And then you can still see that we still have a 10-foot separation to the gate. Because technically somebody can walk right up to the gate. So we want to keep those unqualified personnel away from the test area. Once again, B is our high pot tester, A is our device under test, C is our operator, and then D is another insulation mat. So in this case, we basically have gated off the whole area just to make sure that nobody can come in there and that only the qualified guy labeled C is in there running the tests. Now here's an actual picture. A customer was kind enough to let us take a picture of their setup, and I think they have a very good setup here. Now they have the luxury of testing something very small. And as you can see in the bottom of the picture there, they have a fully enclosed plexiglass enclosure for their testing product. All their high pot test equipment is labeled up top, is put up top on those shelves, so there's no easy access. And you can see yellow tape on that bench. You can kind of see it in the bottom side of the picture, but their entire floor is taped off as well. So only the qualified operators should be in that particular setup. Now later in the year, we are going to have another webinar that is going to specifically talk about attributes that qualified workers should have to work in such a setup. But we simply don't have time to cover that here. So let's look at a couple additional methods for safety. Like I said, there's a lot of ways you can do this. Here's another one, dual remote palm switches. These are great because what they make you do as an operator is you have to have your hands on the switches all the time in order for the unit to be outputting voltage. First of all, you have to activate them both within 0.5 seconds. So you can't cheat and put one hand on one and then put your foot on the other one, because you probably wouldn't be able to do that within 0.5 seconds. If you don't activate them within that small window, the unit simply won't output voltage. So you basically need simultaneous activation. You also want to separate them by at least 21.6 inches. What that allows for is that somebody can't cheat and use the same hand to activate both switches. So example, putting your elbow on one switch and then reaching your hand over and putting it on the other switch. If somebody's got a forearm and fingers longer than 21.6 inches, that is a very large individual. Maybe for that guy, first of all, he'd probably be playing basketball. Secondly, you probably want to separate them even more. It's for each user's discretion, but that 21.6 inches or 550 millimeters actually comes from a testing standard that I'll mention in a little bit. It also does not allow contact with the DUT because you have to have both switches simultaneously activated throughout the entire duration of the test for the test to run. And I'm going to show you a video example of that as well coming up. And you guys saw this in my two previous images when we were showing both of the test stations. It's a tower light. There's a lot of different ways you can use a tower light. Basically, it'll illuminate red either when a test is in process. I've even seen some people, if the high pot tester is even on, it's red the whole time the high pot tester is on, and it's only green when your high pot testing station is shut down. Basically, if the high pot tester is in a ready state, they have it on red. I've seen some guys, they do it where it's yellow in that state and then it's only red while it tests. It's really how you want to set it up. You have some flexibility there, but it is an option for you. And I usually see these mounted way up high on a production floor. It's not really for the test operator. He knows when he's going to run the test. It's for the guys around that might not know he's running a high pot test. So if he sees, oh, hey, the light's red, Jim's working on a high pot test, I better wait till that's over before I go in there and talk to him. And then, of course, as you saw in the previous pictures, insulation mats. I have 2 of them here in my lab. And when I'm running tests, I'm standing on them the whole time. It's just a really easy way to isolate you from ground and a simple way to keep your operators safe. So bear with me here, guys, because like I mentioned, we're using a new service. So I'm going to have to share my videos with you. So I have a couple videos here that are showing various conditions for testing. So bear with me here for a second. I'm going to pause this and make sure we start from the beginning. All right. So you guys should, at this point, be seeing a video I have it on pause, but this is me in the lab, and I'm going to show you a couple things here. Jim, if for any reason this video doesn't look like it's working out, please feel free to chime in. If I don't hear from you, I'm going to assume it's flowing perfectly. So I'm going to not press pause, but you can see the first thing I'm pointing at there is the light. I have a tower light in the lab, and I run it right here where if the HiPot tester is on, that light is red, just to show that the HiPot unit is always in a ready state. So you can see I'm going to point at the light, and that's what I use to let people around me know that I'm about to run a HiPot test. This is my DUT enclosure. So as you can see, I have the door open, and I have my testing product in the enclosure. And I'm not going to show you connections or anything. We're going to save that for the next webinar. The important thing is I have my DUT hooked up inside the enclosure. So I'm going to shut the door, which is wired directly to my interlock on the back of the HiPot. So I have those doors wired with a magnetic switch across pins 4 and 5 on my HiPot unit. And that ensures that if that door opens, the unit's going to not output voltage. So as we'll see here, I'm going to start the test, but mid-test, about 3 seconds in, I'm going to open the door, the DUT enclosure door. Right there, the unit said, hey, your door's open, I'm stopping the test. So even by the time I open that door and try to touch the DUT, even if I did it as fast as I could, this HiPot tester, this particular one, is going to just discharge within 0.2 seconds. So it discharges really quick. It doesn't give me enough time to do it, mitigating the shock hazard greatly. So now I'm going to close the door, push the test, and let it go through the entire test. And as you can see, if I keep the door closed, it passes. So now in my next video here, I have a slightly different setup. Now as you can see, I have it paused once again, just to kind of explain what's going on here. As you can see, my light is still red. On the right-hand side, you can see we have a DUT that's a little bit bigger. So it didn't fit in my enclosure. This is pretty common. Unless you have a custom-built enclosure, a DUT might not fit. So what I'm doing here instead is using two-hand controls. And you can see them on the left-hand side near the middle of that test bench. I have them spread apart. That's much wider than 21 inches. You'll see in the video I'm standing kind of awkwardly off to the side, but that's because I wanted to give you guys a good feel for what I'm doing here and show you. What you can't see in this video is I do have insulation matting on the floor there. So even though I'm using these other safety measures, I'm still using my insulation mat. And this particular lab, the door that goes into the lab, has a danger high voltage sign on the door. The nice thing about the lab is I can keep it completely enclosed off from everybody. So that really mitigates the hazard for anybody else. And only myself and a few other people are qualified to go in here and work with this equipment. But what I'm going to show you here first is I'm going to try to activate these two palm switches in greater than 0.5 seconds of one another. So I'm going to push one, wait, and try to push the other. As you can see, it did nothing. I have to activate them simultaneously. So I tried to push the test button there, but I have my PLC remote activated. So my HiPot test didn't run. I know the screen is a little difficult to see here, but if you look on the HiPot tester, on the bottom right-hand side of the HiPot tester where there's that white, red, and black lead connections, there's a little HV symbol. When I start the test, you'll see that flash indicating that high voltage is outputting. So basically what I tried to do is cheat and push the test button, but I have my PLC remote activated, so it's not going to let me do that. I have to use those switches. Now I'll activate simultaneously, and it starts. However, as you can see, I lifted one hand and still have the other one pressed. The HiPot unit, you can see on the screen, it says abort. I have to keep my hands on the whole time for it to work. So first I'm going to manually reset. Now I'm going to hold them both down, and you can see I have to hold them down for the entire duration in order to keep the HiPot test going. So that's just another example of how you could easily, with just a few different devices, set up your workstation to make it a lot safer for the user, not only the user, but the other people involved as well. So some training resources for you guys. And hopefully you guys can use these. I can point you in the right direction and give you some guidance here. First of all, OSHA. If you're working here in the States, OSHA and NFPA are very important to know. So CFR Part 1910.332 Subpart S. Literally, you could type that into Google, and it'll take you right to that web page. All this information on the OSHA website is free. It defines training requirements for anybody exposed to voltages in excess of 50 volts. These employees must be qualified to work on or near exposed energized parts. Now, I know we didn't get into a huge amount of detail about these OSHA requirements or anything along those lines in this webinar. We have a webinar later in the year in which we will define this further. NFPA 70E, which is National Fire Protection Agency. OSHA bases a lot of their stuff off of this particular document. It's a book. You can buy it. It's not very expensive, and I recommend that you have the most updated version, which I believe is 2012, on hand at any time. This explains reasons behind the rules and how to comply. It's safe work practices, PPE, and lockout takeout procedures. It's basically the Bible of safe testing and safe operations in the workplace. So if you have anything along these lines, I highly recommend you have this. And then the BS European Norm Standard 50191-2010. This isn't a U.S. standard. It's not UL or anything like that. It is a British standards, BSI, as is the British Standards Institute, European Norm Standard. So they really only enforce this heavily in Europe. However, it is a great document to reference if you have an electrical safety testing workstation. The great thing about it is, number one, yes, you do have to pay for it, but it's only about 20 pages long. And it's a very short, concise document that gives you great information on how to set up your workstation. And it mentions a lot of the things I've talked about here today. I've been drawing on this material for a long time. So it's basically the erection and operation of electrical safety testing equipment. So basically exactly what we're talking about. It defines recommended setups for electrical safety testing stations. And the great part about it, it doesn't just talk about production line. It talks about different lab environments, temporary testing environments. They only need to test once a month. It tells you how to do that too. So it covers a lot of different cases. Again, if you want copies of these slides, let Jim know, because he can get you a copy so that you have these resources available. There's also additional training resources on our website. We have a webinar archive. We have an operator's guide. We have tons of different white papers and technical articles. So take a look at our website. Look at our resources. You can find a wealth of knowledge there. You can also feel free to contact us. We're always happy to talk to you guys about this kind of stuff. So if you email us at info@asresearch.com, we will direct your question to the proper person. It'll probably be either Syed, myself, or our technical services manager, Dwayne Davis. Dwayne has been here for 45 years. If there is a question about HiPod testing that he doesn't know, the answer doesn't exist. So keep that in mind. We have a lot of experience in-house, so feel free to reach out to us. That is the end of the webinar. So I'm going to leave it open for a few minutes to any questions that we might not have been able to get to during the webinar. First and foremost, I really appreciate your guys' attendance and your patience in dealing with any hiccups that we might have had for this webinar. Our next webinar will be the complete overview part 2, where we will cover the different safety testing types and how you can run these tests. So then we're going to get into a little bit more technical detail about the tests themselves, but we basically felt it necessary to cover the safety aspect first. Once again, thank you very much and have a great day. Real quick here, guys, I do see some information. Somebody asked a question about the 10-foot distance and best practices, and I see somebody answered OSHA website is the best resource. That is true. The OSHA website, that 1910-332 subpart S does define some of that information, but as far as safety approach distances, the NFPA actually has guidelines. It's a table that shows you the different voltage levels and the different approach boundaries for qualified and unqualified workers. So take a look at the NFPA and NEC regulations for that, and you can get the table of safety approach boundaries for different voltages that you would be working with. I also see another question on here. When is the second part of this webinar? That'll be March 12th. And that'll be presented by Syed Avidi, who is our applications engineer. He's great with this stuff, so I highly recommend if you attended this one and found it useful, attend the next one to get more information on the tests themselves. That looks like it does it for the questions. Like I said before, if you didn't get your question answered or you think of something later, just give us a shout. We'd be more than happy to help. Thanks again, everybody.